Critical takeaways from the source materials include decision style examination. The exam requires candidates to identify the most appropriate AI solutions based on specific technical and business constraints, such as cost, latency, and data sovereignty. Transition to agentic AI. A significant shift is noted from standard generative AI, content creation, to agentic AI, autonomous orchestration, and multi-step reasoning. Safety and governance. Responsible AI deployment necessitates the use of human-in-the-loop (HITL) workflows, approval gates for production rights, and rigorous PI redaction. Operational integration. AI is synthesized across the entire software development lifecycle, SDLC, from automated requirements gap analysis to code scaffolding and synthetic test data generation. Generative AI models and architectural patterns. Core model families. AI systems are categorized by their primary functional strengths and architectures. Large language models, LLMs optimized for natural language understanding, summarization, and theme extraction from unstructured reports. Convolutional neural networks, CNNs specifically engineered for image recognition and spatial pattern detection, such as analyzing network topology diagrams. Diffusion models, designed to generate high-fidelity images through iterative noise reduction. Multimodal models, capable of processing disparate data types simultaneously, such as analyzing configuration logs alongside a physical rack photo. Retrieval Augmented Generation, RG. RAG is a design pattern that mitigates LLM limitations, such as hallucinations and knowledge cutoff stale data. Mechanism. It combines LLMs with external knowledge by converting queries into embeddings, numerical vectors representing semantic meaning, and searching a vector database. The workflow: query processing, retrieval, similarity search, augmentation, adding context to prompt, generation. Benefit: enables models to utilize proprietary or real-time data without the prohibitive cost of continuous retraining or fine-tuning. Deployment and economics. Hosting trade-offs. Cloud-hosted APIs offer rapid elastic scaling for unpredictable demand, while local/on-premise deployments provide maximum data sovereignty and privacy for proprietary source code. Token economics. Costs are driven by token consumption. Practitioners must manage the context window, the maximum tokens a model can process, to prevent the loss of earlier conversation data and minimize financial costs by reducing input prompt size. 2. Advanced prompt engineering. Effective communication with AI models requires structured techniques to ensure output reliability and technical depth. Technique. Description. Purpose. Persona definition. Assigning a specific role, e.g., senior network architect. Guides tone, vocabulary, and technical depth. Describing the situation. Providing background, environmental details, and constraints. Grounds the AI in the specific reality of the project. Few-shot prompting. Providing 2 to 3 examples of the desired input-output pattern. Establishes a pattern for the model to emulate. Prompt chaining. Breaking a complex task into sequential prompts. Uses the output of one step as the input for the next. Self-consistency. Running the same prompt multiple times to compare results. Verifies the reliability and stability of the output. Mitigation strategies. To prevent hallucinations, fabricated information, practitioners should request citations and ground responses in specific provided technical documents. To prevent infinite loops in autonomous systems, constraints such as maximum iteration limits must be implemented. 3. Agentic AI and orchestration.
Agentic AI.
The sources distinguish between generative AI, which produces content in single-turn responses, and agentic AI, which executes multi-step reasoning loops to pursue high-level goals autonomously. Multi-agent frameworks. Coordinator agent acts as the central management layer. It performs task decomposition, delegates subtasks to specialized agents, and aggregates results into a coherent final response. Deterministic branching, a workflow mechanism where the next step is dictated by pre-programmed rules, if-then logic, rather than model confidence. This ensures predictability in high-stakes environments. Model Context Protocol, MCP. MCP is an open standard for connecting AI applications to external tools and data sources. MCP Client orchestrates the interactions between the AI application and the servers. MCP Server exposes specific tools and resources, e.g., get NetFlow statistics to the AI model. JSON schemas, used to define the required parameters and data types for tool calls, ensuring the agent provides valid inputs that the tool can process. 4. AI in the Software Development Lifecycle, SDLC. AI is integrated across all phases of the SDLC to enhance productivity and reduce logical errors. Requirements phase. AI scans unstructured stakeholder documentation to identify intent, flags logical contradictions or gaps, e.g., missing edge cases, and drafts structured agile user stories. Implementation phase. Code scaffolding generates the initial project structure and boilerplate files from a high-level description. Refactoring identifies design flaws and improves code structure while maintaining original behavior. Testing phase. AI generates comprehensive test cases, positive, negative, and boundary, and creates realistic synthetic test data, with PI masked for compliance. Maintenance and debugging. AI-assisted debugging involves feeding runtime error logs to a model to receive root cause explanations and suggested fixes. Ethics, security, and governance. Responsible AI principles. Fairness requires auditing model outputs for bias to ensure equitable treatment of different user groups. Transparency, disclosing to users when AI is being used, e.g., summarizing support tickets. Human-in-the-loop, HITL, a mandatory safety gate for high-impact actions, such as write access to production databases or authorizing customer-facing communications. Security threats and mitigations. Data poisoning. An attacker contaminates the training set to influence future model behavior. Direct prompt injection. A user enters malicious instructions to override system rules, e.g., ignore previous instructions. Indirect prompt injection. Malicious instructions are hidden in external data sources that the AI retrieves or reads. Data privacy. To protect personally identifiable information, PI, when using public chatbots, practitioners must anonymize or redact sensitive data before transmission, as input data may be used for model training. And machine learning fundamentals. Learning paradigms. Supervised learning requires labeled datasets, input-output pairs, to train models for classification or regression. Unsupervised learning, used when no labels exist to discover patterns or groupings in data. Model evaluation and optimization. Accuracy, the standard metric used to evaluate classification models, measuring correct predictions against total predictions. Overfitting occurs when a model learns training data noise too well, failing to generalize to new data. Regularization, a technique that adds a penalty for complexity during training to discourage overfitting and improve generalization. Data bias. Aggregation bias occurs during data analysis when a summary masks significant subpatterns within specific subgroups. For example, a healthy average latency metric may hide a critical failure at a specific branch office. 7. Cisco Enterprise AI Integration. Cisco utilizes AI across various platforms to enhance network observability and security. Cisco DNA Center uses AI and analytics for intent-based networking and automated operations. Cisco SecureX provides AI-powered security analytics and visibility. Telemetry protocols, NetFlow and gRPC are the primary technologies for streaming telemetry and network observability, providing the data necessary for AI-driven anomaly detection and AIOps. Section 1. Concept Review Quiz. Instructions. Answer the following questions using 2 to 3 sentences. Why is defining a persona considered a best practice in technical prompt engineering? What is the specific role of the client in the Model Context Protocol MCP framework? How does Retrieval Augmented Generation, RG, address the limitations of stale knowledge in large language models? What is the difference between supervised and unsupervised machine learning regarding data requirements? Describe the function of embeddings within a vector database. In the context of AI-driven data analysis, what is aggregation bias and why is it a risk? How does code scaffolding differ from software code refactoring in an AI-assisted development workflow? What is deterministic branching and why is it preferred in high-stakes automation workflows? How can a practitioner effectively mitigate the risk of exposing personally identifiable information, PI, when using public AI services? What are the primary differences between generative AI and agentic AI? Section 2. Quiz Answer Key. Defining a persona guides the AI to respond with a specific role-based tone, vocabulary, and communication style appropriate for the intended audience. This practice ensures the response matches the required level of technical depth, such as a senior architect explaining a concept to a junior engineer. The MCP client acts as the orchestrator that manages communication between the AI application and various MCP servers. It is responsible for initiating connections, discovering available tools or resources, and routing requests for context or task execution. RAG allows a model to retrieve relevant information from external, up-to-date databases before generating a response, rather than relying solely on its frozen training data. This process ensures the output is grounded in current or proprietary information, effectively addressing the knowledge cutoff issue. Supervised machine learning requires labeled datasets where input-output pairs are explicitly defined for the model to learn a mapping. In contrast, unsupervised learning is used when no labels exist, allowing the algorithm to discover patterns or groupings within the data autonomously. Embeddings represent data numerically as vectors in a high-dimensional space to capture semantic meaning rather than just keyword matches. They allow vector databases to perform similarity searches, retrieving information that is conceptually related to a user's query. Aggregation bias occurs when high-level summaries or combined data mask significant differences or unique subpatterns within specific subgroups. This presents a risk because a healthy average can hide critical issues, such as a single network branch suffering from extreme latency while the overall average remains low. Code scaffolding involves using AI to generate the initial project structure, boilerplate files, and basic configuration to accelerate the start of development. Refactoring, however, is the process of using AI to analyze existing code to identify design flaws and improve its internal structure without changing its external behavior. Deterministic branching is a decision point in a workflow where the next step is dictated by specific, pre-programmed rules rather than AI judgment or probability. It is preferred in high-stakes environments because it provides predictable, repeatable, and auditable outcomes that are safer for production. The most effective strategy is to anonymize or redact PI from the dataset before transmitting any request to the public AI service. This ensures that sensitive information never leaves the organization's controlled environment, preventing it from being used for model training or exposed in a breach. Generative AI focuses on creating content or responses based on a single prompt in a single-turn fashion. Agentic AI is goal-oriented and capable of planning, reasoning, and executing multi-step workflows by autonomously using external tools and iterating until an objective is met. Section 3. Essay Format Questions. The role of AI in the requirements phase. Discuss how AI enhances the requirements phase of the software development lifecycle, SDLC. Focus on its ability to analyze stakeholder documentation, identify logical inconsistencies, and draft structured user stories, while explaining the necessity of the human-in-the-loop principle. Mitigating security risks in enterprise AI. Analyze the threats of data poisoning and prompt injection, both direct and indirect. How do these attacks influence model behavior, and what specific defensive strategies should a technical practitioner implement to secure an AI deployment? Evaluating model selection and deployment. Compare the trade-offs between cloud-hosted AI APIs and local LLM deployments. Consider factors such as term, definition, AI apps. The application of AI to improve IT operations, automate monitoring, detect anomalies, and accelerate incident troubleshooting. Approval gate. A mechanism in an automated workflow that pauses execution to apply human judgment before a high-impact action is performed. Chain of thought. A prompting technique that encourages the AI to think step by step, improving its reasoning for complex tasks. CNN, Convolutional Neural Network. A model family optimized for image and visual pattern recognition, such as analyzing network topology diagrams. Context window. The maximum number of tokens an LLM can process at once. Exceeding this limit causes the model to lose the earliest parts of the text. Data poisoning. An attack where a malicious actor contaminates a model's training set to influence its future behavior or output. Deterministic branching. A predictable decision point in a workflow where the next step is chosen based on strict, predefined rules. Diffusion model. A generative model family designed to create high-fidelity images by iteratively reducing noise until a coherent image is formed. Embeddings. Numerical vector representations of text or objects that capture semantic and conceptual meaning in a mathematical space. Few-shot prompting. A technique where a user provides a few examples of the desired input-output pattern within the prompt to guide the AI's response. Fine-tuning. The process of training a pre-trained model on specialized data to adapt it to a specific domain or business use case. gRPC. A protocol commonly used in modern network automation for efficient, real-time streaming of telemetry data. Hallucination. A phenomenon where an AI model confidently generates information that is false, fabricated, or unsupported by its source context. Human-in-the-loop, HITL. A governance requirement ensuring a qualified person reviews and validates AI-generated decisions in high-stakes environments. Knowledge cutoff. The point in time after which a model has no information from its training data, potentially leading to outdated responses. MCP, Model Context Protocol. An open standard for connecting AI models to external tools and data sources via clients and servers. NetFlow. A Cisco technology used for network observability and telemetry, providing visibility into traffic flows for AI-driven operations. NLP, Natural Language Processing. A field of AI focused on enabling computers to understand, interpret, and generate human language. Prompt chaining. A technique where a complex task is broken into sequential prompts, with the output of one becoming the input for the next. Prompt injection. An attack where a user, direct, or a poisoned data source, indirect, provides instructions that override an AI's safety filters or original logic. RAG, Retrieval Augmented Generation. An architecture that combines an LLM with an external retrieval system to ground responses in current, relevant data. Regularization. A technique used in machine learning to prevent overfitting by discouraging models from becoming overly complex and memorizing noise. Tokenization. The process of splitting text into smaller units, tokens, for processing by an LLM. It is often the basis for AI usage billing. Vector database. A specialized database designed to store and search embeddings, enabling fast semantic retrieval of information. PI protection in public AI services. Expanded study notes. Question explanation. Cisco 810-110 ATEC, AI ethics and security. Which approach best protects PI when using public AI services? Correct answer, C, anonymizing or redacting PI before sending. YC is the strongest protection. Anonymizing or redacting PI means removing, masking, or replacing sensitive personal identifiable information before the data ever leaves your environment and reaches a third-party AI provider, e.g., OpenAI, Anthropic, Google, etc. Practical techniques include replacing names with placeholders, e.g., customer_name, masking account numbers, SSNs, IP addresses, email addresses, removing entire sensitive fields entirely, using tokenization or pseudonymization. Key advantage: even if the AI provider suffers a breach, logs the conversation, or uses the data for training, the real PI is never exposed. This is a preventive control at the data source. Why the other options are weaker. A. SOC 2 compliance. This is a good organizational assurance that the AI provider has security controls, but it does not stop your data from containing PI when it is sent. It's provider-level trust, not direct protection. B. System prompts to ignore fields. Prompt-based instructions, e.g., do not store or remember any PI, are unreliable. LLMs can still hallucinate, log, or leak data. This is considered a weak, easily bypassed control. D. Encrypting payload in transit encryption, TLS/HTTPS, protects data while traveling across the network. However, once the data reaches the AI provider servers, it is decrypted and processed in plaintext. It does not protect against provider-side risks. Enterprise and Cisco context. In real-world deployments, especially with Cisco AI tools or integrated public LLMs, redaction is part of a defense in-depth strategy. Organizations often combine pre-processing pipelines, redaction layer, private endpoints or VPC peering, data classification policies, audit logging of what was sent. This aligns with responsible AI principles emphasized in the exam, privacy by design. Exam tip: expect scenario-based questions in the ethics and security section. The key takeaway is that you control what leaves your environment. Redaction/anonymization is the most direct and effective method when using untrusted/public AI services. Hosting strategy and data sovereignty. Expanded study notes. Question: which hosting strategy gives the highest data sovereignty? Correct answer: D. Local LLM on internal hardware. What is data sovereignty? Data sovereignty refers to the full legal and operational control an organization has over its data, including where it is stored, who can access it, and how it is processed. This is especially critical for regulated industries, finance, healthcare, government, and when dealing with sensitive data such as PI, intellectual property, or proprietary network telemetry. YD is the best answer. Local LLM on internal hardware, also called on-premises or self-hosted deployment, provides the highest level of data sovereignty because Data never leaves your organization's controlled environment. You own the physical or virtual infrastructure, servers, GPUs, air-gapped networks. No third-party provider has access to raw data or model interactions. Complete governance over updates, logging, auditing, and data deletion. Typical setup. Models like Llama 3, Mistral, or Phi 3 running on internal clusters, using tools such as Llama, VLLM, or Hugging Face text generation inference. Often combined with private vector databases and RAG pipelines. Enterprise and Cisco context. In Cisco environments, high data sovereignty is often required for secure network operations, telemetry, configuration data, compliance with regulations GDPR, CCPA, IDR, CMMC, air-gapped or highly secure deployments, defense, critical infrastructure. Many organizations start with hybrid for convenience and scale, but move sensitive workloads to local LLMs when sovereignty or latency requirements are strict. Trade-offs to remember. Pros of local: maximum privacy, lower long-term cost for heavy usage, reduced vendor lock-in. Cons of local: requires significant compute investment, GPUs, expertise for deployment/maintenance, and potentially slower scaling. Local LLM on internal hardware. Why it's correct for highest data sovereignty. Short answer: Option D is correct because it gives your organization complete, uninterrupted control over both the data and the AI processing environment. Detailed explanation, semi-technical. Data sovereignty means having full legal, operational, and technical authority over your data, where it lives, how it's processed, who can access it, and how it's protected. Here's why local LLM on internal hardware wins. Zero data exfiltration risk. All data, inputs, prompts, outputs, embeddings, vector stores, stays entirely within your organization's firewall or air-gapped network. Nothing is sent to external cloud providers. Full infrastructure control. You own and manage the physical or virtual servers, GPUs, storage, and networking. You decide security policies, access controls, logging, patching, and monitoring. No third-party trust required. Unlike cloud or SaaS options, you don't have to trust another company's security practices, employees, or legal jurisdiction. Ideal for highly regulated environments, government, finance, healthcare, defense. Compliance advantages. Easier to meet strict regulations such as GDPR, CCPA, HIPAA, IDR, or CMMC because data never crosses borders or leaves your controlled environment. Full auditability of every interaction. Quick comparison: why others fall short. A. Cloud with zero retention. Data still leaves your network and is processed in the provider's environment. Zero retention is a promise, not a technical guarantee. B. Hybrid. Some components, often the heavy inference, may still touch the cloud, reducing sovereignty. C. Managed SaaS. Lowest sovereignty. Your data is fully processed and potentially stored, even temporarily, by the vendor. Local deployment. Using tools like Llama, VLLM, Hugging Face TGI, or Private GPT is the only option where data sovereignty is maximized by design. Real-world Cisco context. For network teams using AI for log analysis, troubleshooting, configuration generation, or security operations, running local models ensures sensitive telemetry, customer data, and proprietary configurations never leave the organization, which is often a hard requirement in enterprise and government accounts. Trade-offs: be honest in the exam. Higher upfront cost, hardware/GPUs, and operational complexity. Slower to scale compared to cloud. Requires in-house expertise. Headphone Cisco 810 to 110 AI Technical Practitioner. Real Knowledge 45-minute audio study guide. Core concept in multi-agent systems, A coordinator agent, sometimes called an orchestrator or supervisor agent, serves as the central management layer. It does not perform all the work itself, but intelligently directs the overall process. How it functions, correct answer, A. A coordinator agent orchestrates task delegation and aggregates outputs. Detailed breakdown. Task decomposition takes a high-level goal and breaks it down into smaller, specialized subtasks. Agent selection and delegation routes each subtask to the most appropriate specialized agent, e.g., a network analysis agent, a data retrieval agent, or a code generation agent. Workflow control manages execution flow, sequential, parallel, or conditional, and handles dependencies between tasks. Result aggregation collects outputs from individual agents, resolves conflicts or inconsistencies, and synthesizes a final coherent response. Monitoring and iteration tracks progress, reassigns tasks if an agent fails, and iterates when needed. Why this matters for enterprise and Cisco contexts. Enables scalable solutions for complex network operations, troubleshooting, policy optimization, or automation workflows. Improves reliability and modularity compared to single-agent approaches. Common in frameworks such as LangGraph, CrewAI, AutoGen, and agentic Cisco ecosystem tools. Real-world example request. Optimize WN performance across 5 sites. Coordinator breaks it down. Agent 1 analyzes current traffic logs. Agent 2 reviews QoS configurations. Agent 3 runs predictive simulations. Coordinator merges findings and delivers a prioritized action plan. Key benefits. Better fault tolerance and load distribution. Easier debugging, trace which agent contributed what. Higher quality outputs through specialization. Common pitfalls. Coordinator becoming a performance bottleneck if poorly designed. Excessive communication overhead between agents. Need for clear protocols, tool calling, message formats. Exam tip focus on understanding roles in multi-agent architectures rather than low-level code. Expect scenario-based questions on when to use a coordinator versus fully autonomous or hierarchical agents. Let me know if you'd like this integrated into a full set of clean text notes, more practice questions, or expansions on related topics like React agents, tool integration, or LangGraph implementations. Retrieval Augmented Generation, RG, expanded explanation. As an AI agent operating within a multi-agent or enterprise framework, I'll break this down clearly and semi-technically for your Cisco 810 to 110 ATEC prep. What RG means. Retrieval Augmented Generation, RG, is a design pattern that combines the strengths of large language models, LLMs, with external, up-to-date knowledge sources. Instead of relying solely on the model's internal parameters, which are frozen after training and can become outdated, RAG allows the model to retrieve relevant information from external databases before generating a response. Primary goal, correct answer, B. Improve model responses with external knowledge. This directly addresses 2 major LLM limitations. Hallucinations, making up plausible but incorrect information. Stale knowledge, models only know what they were trained on. How RG works, step by step. Query processing, user question comes in. Retrieval stage, the system converts the query into an embedding, vector representation, and searches a vector database, e.g., Pinecone, Face, or Chroma, for the most semantically similar documents or data chunks. Augmentation. The retrieved relevant information is added to the prompt sent to the LLM. Generation stage. The LLM generates a response using both its internal knowledge and the fresh external context. Why this matters for the exam and enterprise use. Enables more accurate, Trustworthy AI systems, critical for Cisco networking scenarios like troubleshooting, policy analysis, or configuration recommendations. Supports real-time or proprietary data, company docs, latest network telemetry, Cisco best practices that the base model doesn't have. Reduces the need to constantly retrain or fine-tune large models, which is expensive. Business/technical benefits. Higher response quality and factual accuracy. Better handling of domain-specific knowledge. Improved traceability. You can see which documents were used. Cost-effective compared to continuous model training. Common implementation tools. LangChain/Llama Index, popular frameworks. Embedding models, e.g. from Hugging Face. Vector stores for fast similarity search. Exam tip. Expect questions testing your understanding that RG is about augmenting generation with retrieval, not replacing models, reducing compute, or handling encryption. It's a key technique in the generative AI models section, 20% weight. In a retrieval-augmented generation, RG, system, embeddings are the bridge between human language and mathematical processing, allowing AI to understand the conceptual relationships between different pieces of information. Here is a more detailed breakdown of how they function and why they are essential. 1. Beyond keywords, capturing semantic meaning. Unlike traditional search engines that look for exact keyword matches, embeddings represent the semantic meaning of text. For example, a keyword search might miss a document about routers if you search for networking hardware, but an embedding-based system understands that these terms are conceptually related because they occupy a similar neighborhood in a high-dimensional mathematical space. 2. Numerical vectors and high-dimensional space. Numerical vectors. An embedding is essentially a long list of numbers, a vector. Each number in that list represents a specific feature or dimension of the text's meaning. High-dimensional space. These vectors are placed in a complex mathematical space. Concepts that are similar, like OSPF and BGP, will have vectors that are physically close to each other in this space, while unrelated concepts like VLANs and HR vacation policy will be far apart. 3. Their role in the RAG workflow. Embeddings are the core of the retrieval stage in a RAG system. Storage. Before a user even asks a question, your technical documents are broken into chunks, converted into embeddings, and stored in a vector database, such as Pinecone or FASS. Retrieval. When you submit a query, the system converts your question into an embedding. Similarity search. The system then performs a similarity search to find the data chunks in the database whose embeddings are mathematically closest to your query's embedding. This ensures the AI retrieves the most relevant information to answer your specific question. 4. Importance for accuracy and reliability. In the context of the Cisco 810-110 exam, understanding embeddings is vital because they directly impact the quality of the AI's response. Reducing hallucinations. By retrieving mathematically relevant facts from your own proprietary data, like Cisco manuals, through embeddings, the model is grounded in reality rather than relying on its generic training data. Handling unstructured data. Embeddings allow LLMs to effectively summarize and extract themes from thousands of unstructured reports by recognizing recurring patterns in the semantic space. Aggregation bias occurs in data analysis when researchers or AI models rely too heavily on summarized or combined data, which inadvertently conceals significant differences or unique patterns within specific subgroups. In the context of the Cisco 810-110 exam and technical practitioner workflows, here is a more detailed breakdown of this concept. 1. The masking effect of summarization. The core danger of aggregation bias is that a high-level summary may look accurate on average, but fail to represent the reality of smaller groups. For example, if a network analyst looks at the average latency, Across an entire global enterprise, the summary might look healthy, e.g., 20 milliseconds. However, this summary could mask the fact that one specific branch is suffering from 500 milliseconds latency, while others are at 5 milliseconds. 2. Impact on exploratory data analysis, EDA. In the four-step EDA methodology, orient, hypothesize, correlate, visualize, aggregation bias is most likely to strike during the orient phase. Because the goal of orienting is to generate a high-level summary of feedback or telemetry, a practitioner might settle on an initial hypothesis based on that summary alone. If the summary is biased through aggregation, the subsequent hypothesize and correlate steps will be based on a flawed foundation, leading to incorrect technical conclusions. 3. Ethical and governance risks. Aggregation bias is categorized under ethics, security, and responsible AI because it can lead to inequitable outcomes. Algorithmic bias. If an AI model is trained on aggregated data that masks the needs or behaviors of a minority subgroup, the resulting model may perform poorly or unfairly for that group. Bias mitigation. To combat this, technical practitioners are encouraged to perform regular audits for bias and ensure that AI-generated insights are validated through human review to catch these hidden subpatterns. 4. Why it matters for AI systems. In AI-assisted data analysis, models are often used to synthesize thousands of unstructured reports or logs. While LLMs are excellent at identifying recurring technical themes, they can fall victim to aggregation bias by over-prioritizing the most frequent, average themes and ignoring critical, edge case subpatterns that only appear in a small fraction of the data. Key takeaway. To avoid aggregation bias, you must look beyond the top-line statistics and use AI to specifically cluster and segment data into subgroups before performing a final analysis. In the software development lifecycle, SDLC, the requirements phase, also known as planning and analysis, is the most critical stage for using AI to refine documentation and translate business needs into technical tasks. While traditional requirements gathering involves manual stakeholder interviews and workshops, AI significantly enhances this process by automating the heavy lifting of information synthesis. Here is a detailed breakdown of how AI functions in this specific SDLC phase. 1. Stakeholder documentation analysis. Technical practitioners use large language models, LLMs, and natural language processing, NLP, to scan vast amounts of unstructured data, including meeting transcripts, stakeholder emails, support logs, and legacy project documents. The AI acts as an initial filter to extract intent and organize raw feedback into a coherent starting point for developers. 2. Detection of logical inconsistencies and gaps. One of the most valuable roles of AI in this phase is identifying blind spots that a human might overlook. Contradiction spotting. AI flags logical contradictions where one stakeholder's request conflicts with another's. Gap analysis. It highlights missing edge cases or incomplete requirements, such as a feature that lacks a defined payment method for international users. Compliance alignment. AI can cross-reference drafted requirements against regulatory frameworks to identify potential conflicts early in the cycle. 3. Drafting structured user stories. AI can automatically convert complex business needs into structured agile artifacts, such as user stories. This involves formatting requirements into the standard template, as a user, I want feature, so that benefit. Beyond the stories themselves, AI can also suggest acceptance criteria to define what done looks like for each task. 4. Strategic benefits for technical teams. Integrating AI into the requirements phase offers several enterprise advantages. Efficiency. It can reduce weeks of manual documentation work down to a few days. Prioritization. AI can suggest the priority of specific user stories based on business value, technical risk, or the frequency of stakeholder requests. Grounding through RG. By using Retrieval-Augmented Generation, RG, technical teams can ensure the AI drafts stories that are grounded in the organization's specific proprietary standards and past project history. 5. The role of human in the loop. Despite the efficiency of AI, the sources emphasize that this phase requires a human in the loop (HTL) approach. AI is used to draft and identify issues, but a human expert must provide the final validation to ensure the user stories accurately reflect the project's high-level goals before moving into the design and implementation phases. A strong use case for generative AI in the testing phase of the SDLC is automated test case generation and test data creation. Quick context on the testing phase. In the software development lifecycle, SDLC, the testing phase focuses on verifying that the software meets requirements, functions correctly, and is free of critical defects. This includes unit testing, integration testing, system testing, regression testing, and performance testing. Traditionally, this is labor-intensive, time-consuming, and prone to gaps in coverage. How generative AI fits in. Generative AI, e.g., models like Grok, GPT-4o, Claude, or specialized tools such as Tesdim, Applitools, or GitHub Copilot can significantly accelerate and improve this phase by primary use case, intelligent test case, and test data generation. Input. The AI receives requirements documents, user stories, API specifications, OpenAPI/Swagger, database schemas, or existing code. Output. It automatically generates comprehensive test cases, positive, negative, edge, and boundary cases. Realistic synthetic test data, including personally identifiable information masked data for compliance. Automated test scripts, Selenium, Playwright, Cypress, JUnit, PyTest, etc. Example in practice. A development team building a fintech application needs to test payment processing. Instead of a QA engineer manually writing hundreds of scenarios, they feed the AI the user story plus API spec. The model generates happy path tests, successful payment. Failure scenarios, insufficient funds, expired card, network timeout, fraud detection triggers. Data sets with varied currencies, amounts, and international formats. Regression